John. Good evening, everybody. It's a great pleasure to welcome everybody to the September U3A talk, and a particular welcome to Rosemary, who I'm introducing this evening, but she needs a little introduction to most of us because we all know her as a member of the U3A and, of course, a resident here at Waterfall Hills. But many of you mostly don't know her history, and she's got a very esteemed history. She undertook her education at Rodin and at Wits. And at Wits, for her bachelor's degree, she majored in geology and botany, which is quite an unusual combination, but has stood her in good stead ever since. She subsequently did a master's and a PhD at Wits and has worked in the coal field for over 50 years. But I think many of us will agree that her most notable achievement is marrying Lionel, and hence forming the brand name the Falcons, because they operated together. Lionel's a mining engineer, and they operated together for many, many years in the field of coal science and technology. And in particular, for over 20 years, they worked together at Wits, where they supervised well over 80 master's and PhD students, and lectured to well over 2,000 students as part of their course in coal mining and science and technology. Rosemary was appointed professor, and I'd like to actually explain what a bit more detail here, because she was appointed a SARCI professor. Now, SARCI is the South African Research Initiative, Chair Initiative, by the NRF, the National Research Foundation. And to get such a chair, you have to be top of your field. And this shows that Rosemary is really top of her field in the subject of coal, and specifically clean coal. She retired from her professorship in 2018 and is now an emeritus professor at Wits. But during her career, she's had many awards: a gold medal from the South African Institute of Mining and Metallurgy, the Draper Award from the Institute of Geology, and also an award from an international organization. So she's very, very, very well qualified to talk about the subject which we have for her tonight. And without further ado, Rosemary, over to you.
Thank you very much indeed. My goodness, can you hear me, Rob? Are we loud and clear?
Yes, Rosemary, you are.
Oh, that's fine. Thank you very much indeed. Rob, thank you for your kind words. It wasn't necessary, but it was very kind of you to mention that. Well, thank you so much for inviting me to chat to everybody, and hello to all our good friends. We've had some fun with this topic because I was told from the beginning by a couple of our good friends that it mustn't be technical. Well, when you talk about Eskom and blackouts and load sharing and all the rest of it, you can't help but be a little technical from time to time. But I did manage to find some pretty pictures. And John, if you can help me, I would like to put up my slides. Is that in fact on? John?
No, not yet, Rosemary. You need to push the green button on the share screen on the bottom of your screen.
All right, let me just put that down. The share button, put that up.
It's coming.
There we go.
There you are. Now you just need to start your presentation.
How's that? How's that?
That's perfect.
Is that okay?
That's perfect.
All right, John.
Everybody can see that.
Thank you very much indeed. That's super. Well, we came to the title of The Gardens of Long, Long Ago, the origin of plants and their impact on today. As you heard, I started life as a geologist and a botanist, so you'll understand the combination together becomes quite an important one. Now, as far as this is concerned, I thought we'd have a little trot through history first and then start to look at some of the plants of long, long ago. First of all, the birth of the Earth is 4.8 million years ago, and as it cooled down, it spewed lava and was bombarded by meteorites and comets. This is a fun diagram, which if you can see, I don't know if you can see my cursor. Can you see my cursor, John? I hope you can. The cursor at the bottom, the diagram starts at the bottom, and you have bubbling lava, which eventually solidified and created a crust with craters. Then the first water arrived, and by about 3.8 billion years ago, the first living cells, bacteria, began to exist in the ancient sea. After much more time, we eventually arrived at the green algae that evolved, and after much more time, we eventually get the sea creatures evolving, simple soft-bodied then shell-covered creatures, and about this time, which is 500 million years ago, plus or minus, you actually get complex marine fauna, and then ultimately a little bit of plants tiptoeing onto land. And during this period of time, plants grew and evolved, and you get at this point forests of the northern hemisphere during the Carboniferous, when the coal swamps were forming. At the same time as those coal swamps were forming in the northern hemisphere, we had a massive ice sheet in the southern hemisphere. Forests only occurred in the southern hemisphere in the Permian a little bit later. Thereafter, the climates changed massively. Evolution evolved. We had the age of the dinosaurs. And then about this particular time, 100 million years ago, which is quite young when you think about 4.8 million, we had mammals, flowering plants evolving. Then we come to the last 10 million years. We had volcanics, an ice age, the Pleistocene ice age that we're just coming out of now. And that solid line that you see on the right there is the age of man, the age of man. Now, if I take you through the ages of the Earth, you might find it interesting to relate it to the rocks that you're familiar with. From the 4.8 million, you have the Archean, which is 3 billion to 4.8 billion years. The Proterozoic, which is the beginning of more life than it was in the Archean, 500 to 3 billion years ago, 500 million to 3 billion. Then you have what is called the Phanerozoic, which is where life explodes, roughly 0 to 500 million years, not billion, million years, quite young in the nature of things. Now, we go through ultra-simple cells at the beginning, simple marine bodies, multicellular marine bodies, life in the sea, life on land, advanced plants and animals, and then advanced life, primates to man, dinosaurs, ice age, etc. So we actually have, if you look at the system of rocks in the middle here, virtually we are unbroken from the beginning of the Earth, where the very earliest granites, which incidentally you might like to see at the country club at Woodmead, are some of the oldest granites in the world, followed by the Barberton system, which in fact has the green stones. Then you had the Witwatersrand system with the gold mines. Then you had the Transvaal system with the Cradle of Mankind caves, when the cave rocks were laid down. Ultimately, the Cape system was the first system that came into where life began to explode. Pardon me. We then had this massive ice age, which is called the Dwika Ice Age, which lasted over us for about 80 million years, followed by the deposition of the Karoo system. Now, the Karoo system we all know by driving over the Karoo from Joburg to Cape Town. This hosts the coal fields and obviously gave rise to the Drakensberg Mountains. So it's quite a well-known system. It covers 2/3 of the entire land mass of South Africa. The more recent sediments are the Kalahari. So we have quite a lot to do. Now, in the Phanerozoic, we then have at the bottom, I'm not going to bother you with all these periods, but I'm going to concentrate on those two in the middle. In this Phanerozoic, you have life in the sea, early plants, and the modern floras. This is marine life. These are the first forests, reptiles, dinosaurs, mammals, and humans. Now, the story in South Africa has another twist which you might find of interest, and that is the climate change. From 0 to 500 million odd years ago, we have a climate change which is very dramatic. It goes from the cold, they call it the, as you'll see down at the bottom here, the ice house, as opposed to the hot house. I see that this, there we go. There's the hot house on the right-hand side. So blue means cold weather, pink means hot weather. And over this period of time, we have had 4 major ice ages. This ice age at the top here is the Pleistocene ice age. And as a point of interest, you will see that little curve at the top there, which means we are coming out of the ice age and are warming up quite naturally, apart from anything else. Now, the biggest ice age of all is this particular one. It's the one called the Dwight Ice Age that lasted for 80 million years in the southern hemisphere. And the Karoo system evolved above that. The Cape system occurred below that. Sorry, it seems to have moved down a bit. Right, here's your Cape system. Now, the Cape system occurred in the early stages where you had amazing development within the sea from the sea creatures. Early life. Now, it might interest you to see what type of creatures were there at the time. Right at the bottom here, you have sponges and trilobites, which if you go to any paleontological museum, you will have plenty of those around. Then you have the early octopuses, the early squids. You even have the early snails, and a very strange animal I couldn't find the name for. You also have these very fierce, very large animals. This particular one is called Euryptid. It has claws. You will notice the claws on either side. These 2 animals, well known in the marine environment, were extremely violent and very voracious predators. In addition, you had the beginnings of fish. Now, none of these animals have vertebrates or backbones, but the fish began to evolve, and it was the fish that first began to get a vertebrate column. At the same time, in the Cape system, we have the first tiptoeing onto the land of the early plants, as you can see here. Now, if we move on, the early life during pre-Dwight. Sorry, that seems to be going down. There we go. These are the evidence in the Bockerveld system, sediments in the Cape system. These are fossils that have been found showing the early plants that didn't have the strength to stand up at that time. These are diagrams to show the different species that have been found. Now, directly after that, we have much of Gondwana, Gondwana being all the southern hemisphere continents, covered by this Antarctic-like ice sheet. It's said that we had somewhere between 10 and 12 kilometers of ice above us in various places. Antarctica has nothing compared to what we had. Now, post the Karoo system, we had the explosion of life on land, and it's changed through the times of the Karoo. Now, this is the period we're talking about above the Ice Age. What happens here, you're going, as you'll see from this arrow, from a cold climate as the Ice Age warmed up into a warm climate. And here you have the early plants going from cold, cool, rainforests right the way through to savannas and ultimately to desert and lava flows. You have the fish coming on land and creating the reptiles, amphibia first and then reptiles, and ultimately the very early mammals during this entire period. It is the most productive period of any time in history. And we have this in the Karoo system. Scientists come from all over the world to actually look at the series of evolution at this particular time. Now, if we look a little bit wider as to why these plants are so different to the Northern Hemisphere, let me explain this. Obviously, at that time in the Carboniferous and Permian, talking about 200 to 300 million years ago, the continents were more or less glued together. The northern continents were Eurasia and the southern were Gondwana. Now, in the Carboniferous times, whilst we had this massive ice sheet, much of the area up to the north fell across the equator. So a lot of open shorelines, wide, extensive areas were covered by swamps, and that is where the poles formed in the Northern Hemisphere, whilst we had the Ice Age. This is a reconstruction of one of the plant swamps. This was reconstructed by my colleagues in Germany with whom I trained in the 1970s. They took the plant fossils, they took the environment of the rocks and the coal types, and this is their reconstruction.
Yeah, I know.
Hot,
Now
very
it's saying
hot.
temporary unmuted, but it's still doing nothing for me.
Are you okay there, Pam? Can you hear me? Pam, I think that was you.
Where's my
Anyway, hot, very steamy equatorial swamps. Now here the plants just continue to grow the year round. Very few, some leaves, but more wood falling into these anaerobic and acidic, very deep, not so deep, watery swamps. At the same time as that was happening, we have the Ice Age. This is the extent of that Ice Age during the Dwight times. It's quite interesting to see. It covered most of Africa, portions of South America, all of Antarctica with that exception, India, and then even has been found to some extent in the mountainous areas of Australia at that time. So it was massive. About 300 million years ago, the end of the Carboniferous, the pole, the southern pole, sat over, and we always laugh about this, about Messina. It sat there for many of those tens of millions of years, but very slowly, the axis of the Earth started to move, and the pole moved across to Antarctica. And during this period, you have down here on the left-hand side, a major ice sheet, which began to reduce in size and in fact continued to some extent with interglacial periods at this point, where you had glaciers on the high mountain areas, which then advanced during a cold period and then waned during the interglacial periods here. And I believe very consistently, and I have colleagues who believe with this as well, is that our coal seams formed during these particular periods. As the climate ameliorated, so of course you have the warm, dry period up here. Now, this is the period that I'm talking about. So that is, the upper one is the Carboniferous, the lower one is the Permian, which is about 100 million years later than the northern one. What you have then is the ice concentrated in Antarctica, and you have cold to cool temperate rainforests around that particular area. And you'll see the coal fields in Australia, in India, Madagascar, Southern Africa, and portions of South America, all share the same type of plant and evolution that comes through at that particular point in time, as well as changing climates. This indicates the waning of an ice sheet from glaciers that are now, the ice sheet would have been at the top, and then as that melted, so you actually have the glaciers beneath it beginning to melt as well. Now, there are two reasons why I put this slide in, because it does show what happens at the end of an ice sheet, but it also shows what we have under our feet in the areas of Witbank. Witbank lies above here. Middleburg lies above this particular valley. So if you were to drill way down, you would find coal seams forming in these valleys, and the valleys filling up to being the flat surface that we know when we drive across Mpumalanga and into Limpopo and Mpumalanga. So the second point I wanted to show you is, do you see the dust on the sides? Very fine grained dust on the sides of the mountains. This was scraped by the glaciers going down, and the dust has been incorporated into the glaciers. Now, this is very fine clay, and this, when the glaciers melt, this is what has poured into our coals at the toe of the glaciers. This is why our coals are very high in mineral content. Further down the line, now the ice sheet is gone, you have some glaciers and the land is beginning to appear again. So at the close of an ice age, a wide variety of environments for peat swamps accumulate. This can be in valleys, it can be along seashores, and it can be on deltas. Now this is important because when people are mining and looking to see what quality of coal they have, wherever that coal formed is going to control what type of coal it has in the long end. So coal is not the same from one point to another. Secondly, after the glacier has gone, the absolutely anaerobic barren soil and sand and rocks that have been left by the glacier is infiltrated by lichens and small, simple plants. These then have the job of making organic material in the soil. This provides the substrate for small shrubs to come in. They provide more organic material, which provides the substrate for the larger trees to come in. So there's always a biosuccession at the end of this. This now shows a reconstruction of one of the coal swamps at the end of our ice age. This was developed by my mentor, Dr. Edna Plumstead, who actually has developed and researched all the plants that you see here. Every single one of them has a name and a type. She actually researched around Vereeniging, all the way around the coal fields, got rocks and coal to develop this. What you have in the background is the glacier, very close by. Woodbank will be just up the hill there. What you have, when the glaciers recede, they actually dump lumps of sand and rocks that they've brought down. So you have a very uneven surface. So some plants are growing in dry environments and other plants are growing in water. So it is not consistent from place to place, as the coals of the Northern Hemisphere are extremely consistent from place to place. So that is one of the major differences. Secondly, you'll notice the leaves. All these plants have been colored in the autumn colors. We had long winters and short summers, much as you have up in the northern climates, for example, in Alaska. And we have leaves that have been found in huge banks together, leaves that have dropped off. As a point of interest, do you see that little animal at the bottom of the screen there? That is the only reptile that has been found in the coal-bearing sequences. It's not until much later in time that the animals have been found. It's believed that maybe the animal bones became decomposed in the acidic waters that the coals were forming in. Now, there are parts of the original coal fields that were not in the valleys where you had water, but were on the side of the valleys. Now, there you will find this particular environment. It's an example of a cool to cold temperate forest in Alaska. What you have beneath your feet as you walk there is 5 meters of accumulated woody material underfoot. This is extremely important because it actually behoves the nature of a lot of our coals, which do not exist in Europe and America because they never had dried environments. This gives rise to coals of a very special type in this country. Obviously, being cold climates, we had snow. Now, snow on its own is dry. It is only wet when it melts. So snow covers a lot of the ground, very similar to what you see here at the time of the early stages. As time moved on, ground widened up, the glaciers receded. You have uneven ground with some ponds between them. And the landscape developed even drier plants in certain areas. It began to evolve, the climate began to warm up. And this is very typical of what we call the number 4 seam in the Woodbank area. Later on in time, of course, all the valleys that have now been filled up, the original glaciated valleys have been filled up with sediments. And what you are now looking at is land filled with shale and mud flats. These mud flats do not support coal, they do not support forests, they cannot accumulate, there is not enough vegetation for them to do so. Not only that, it's periodically dry, which oxidizes the muds and sediments in them. And this is the climate in which the reptiles flourished, second to none in the world. This is where the people come to see them. There are something like 8 to 10 different periods of reptiles at this particular scene. Now, it's just something, the coloring here was done specifically because when you drive down to Natal and certain parts of the road going down to Cape Town, you see purple and mauve banding. This is the environment in which it was being formed. Now, as the climate warmed up, more animals evolved. This became less vegetational even. It became dry. This now is representative of the sandstones. We had something akin to the Kalahari sandstone covering us. And that is represented by the cave sandstones in the Drakensberg. And in the Free State. This is the environment in which those sandstones were being laid down. This little animal right in the front here, this tiny little one, is the very earliest mammal at that time. Shortly after that, there was one massive period of volcanism. Lavas poured out not so much as volcanoes, but rather as layers of lava up to 3 kilometers deep. And this is what makes Lesotho the high country that it is. And you see the Drakensberg lavas at the top of the mountains. That is the end of the Karoo. Now, I'm not going to go further than that because it was quite a lot of period beyond that time before the dinosaurs actually appeared. This is all pre-dinosaur time. Now I'd like to show you some of the plants and forests that provided the coal seams as we've seen them today. What you have here is the climate in the blue going through to green and yellow. At the bottom, this is now the 0 to 500 million years. Oh, I beg your pardon, this is the Permian. Subarctic cold climate, fluctuating cold to cool, cool to warm, warm to hot, dry, and then very hot and dry. And then it goes up to the sandstones above that. What you then see with these gray balloons is the flora. These floras began at the very bottom. What you had at the bottom here is the end of the Ice Age. Now, I worked on the very earliest sediments between those final phases of the glaciers, and we found the most beautiful pollens, quite advanced pollens, monosaccharide ones, no plant evidence, no leaves, branches, etc., have ever been absorbed there. Shortly after that, We then did get the shales which represented the early part of the Eka, and then you start getting the trees that are now growing with the wood, the xylem flowing within the tree trunks, and you're getting big trees coming in. The conifers, as the climate changed again, those died out, new ones evolved, all through climate adapted, and became the next group of plants, in this case, the Gangamopterus flora. As that died out, so the Glossopteris, a very famous group of plants in the Karoo, took over, all over the Karoo at this particular point in time. Then there was a major change in climate. This particular point where this gap is, there was in fact a hiatus. Nothing was deposited for a while, and ultimately the last coal seam formed with another new group of flora named the Dicroidium flora. These are the coal seams that formed through these different times. Now it's quite interesting that each coal seam has its own properties, not only because of the plants that it gave rise to or it was derived from, but also because of the climate and the environment in which they were formed. Now, when you're looking at the plants and the flora for evidence, one of the areas is the microflora, fossil pollen and spores in the coal seams. Now, what you have here is the beautiful, clean, polished up forms. They don't all look like that. What we normally do when we look at fossil pollen, I spent many years, that in fact was part of my PhD, was to correlate the coal seams using fossil pollen. You actually take 3 of the 4 most dangerous acids known to man, you literally dissolve away the rocks, and what is left is the organic fossils, which is the pollens and the spores. So what you have here is the cleaned up ones, and they are beautiful. You'll notice this one down the bottom has 2 wings. That's a very simple pollen, but the pollens through that period evolved to very advanced stages. The macroflora, as opposed to the microflora, really relies on leaf impressions, tree trunks, branches, fruits, and flowers. So we now group the whole together, and this is what we see. Now, one of the early major groupings of floras was the Gangamopterus. You'll notice here that it has a very single or simple mid-vein, with lateral veins very simple. In fact, you can hardly even see them. It's a leaf that looks very like the protea leaves at the moment. It is ubiquitous everywhere. It is well known for wherever you do find shales, black shales in the Karoo sediments, you are more than likely going to find leaves like that. Then you see these flowers. Now these come in the Glossopteris flora. That was the next group of major plants that took off. And now your veination, mid-vein, is much more complex. It gives a lot greater strength. These are huge leaves. The trees are now massive. The side veins are very complicated, and different patterns are occurring. Now each different leaf has different species, different genera, and you can actually devise a whole series of plants coming out of this. Then the Dicroidium flora, which was the younger main flora, was made up of ferns. Now these are obviously very complicated leaves that have evolved by this time, and they make up a whole series of types of flowers, leaves that collectively can be found in certain layers in the shales that occurred at that particular time. And then you get this type of plant, which is collectively is a type of fern, but with its own types of leaves. They all have different names. It is an amazing array of plants. I'm only showing you 3 and that little stick one at the top there as examples of what can be found in paleobotany. Now, because we know the leaves were there, I'm now showing you under the microscope what the outer layers or the cuticles of the leaves look like. This is a microfossil What you have is, there may be single, like these ones at the bottom. There may be double, like these ones over here. And they may be thick and waxy or thin and wobbly. You see them layer upon layer upon layer. This is an autumn collection of cuticle leaves at one particular point in time. This particular diagram over here shows a stomata, or a very advanced breathing mechanism for the plant, which is amazing. That took place at about, that would have been about 220 million years ago. The evolution had literally taken off. You also see very large seeds. Now, this is not under the microscope so much as what you can see by hand. We cut and polish. Here you have 3 seeds, and you can see the actual sculpture on the side and underneath here. The central body, it's like taking an orange and taking everything in the orange out, and then squashing it together. And what you have is the open part of the seed where it would burst open over here to the north, or you have this very, very large coat which protects the seeds as it develops. This is a whole series of algae. So we know we had a lot of algae, a bit like the algae that we have in the river. In fact, you probably find there's a very similar species in our little stream that we have. Continuing on, these are the tree rings that showed that we had wonderful seasonal climatic cycles from summer to winter. Amazing, amazing evidence has been found in that regard, including microscopic cell structures of the type of cells that these trees had, and there were a wide variety of them. And some of the twigs and smaller little trees, or saplings if you wish, had structures to build up their strength in this sort of blocked or node system, which you actually don't see in plants today. It was a very early way of trying to build strength in trees and trunks at that time. Quite the most exciting thing of all, despite everything else, was the seed. Now, this is in fact a cone or a fruit that has developed all these little seeds. It almost makes you want to take 1 or 2 of these seeds off and go and plant it in your garden. It's about 2 to 3 centimeters long. On the side, you will see a little wing or a flange going, which would have taken it. Now, these are the little early flowers giving rise to the seeds at the end. Now, this is attached to a Glossopteris leaf. There's a reconstruction on the side there. Now, many different fruits and flowers have been found, and I'm certainly not going to go through all of them. Obviously, they're not colored. They have all been discovered. They've all been researched, and it was the most exciting time for plant development over that period. This is the evolution of the reproductive structures for the male part of the plant. Here's a normal leaf, which then gets an indurated, it's called indurated tip. That tip develops into fructifications or little anthers coming out of it, and that provides you with the anthers which feed the cones which are developing at that time. This, in fact, is your cone, and these are your male, female cone, male antheridia on the side. This is the reconstruction of a Gangamotheris plant. This is how they've actually varied over the time. So you can see, I mean, I've only given you the tip of what has been found in all of this, but this is what gave rise to our coals. This is a reconstruction of the Glossopteris tree. We know the roots, we know the stem when you cut it. Well, that's part of the root. The stem and its blocked node-like nature. We know that it was seasonal. We know all about the leaves. And then we have the fructifications and the reproductive structures on the side. This is the dicroidium plant, the one that was the one at the top, the more advanced one. Now, in this case, it's a fern plant, and you have a very much more advanced female structure, and these are the male structures at the top here. You're almost coming into what we have these days in some of the plants that you see actually around here. Now, just for fun, I threw in an insect wing. A colleague and I found this just a foot or two beyond the last glacial onset. So insects were around very, very early in our Karoo times. And then just for fun, allow me to show you this. This is an example of a fossil plant called Ginkgo biloba. This is the fossil form. This you will find in trees all over Johannesburg. The best ones are in Westcliff Drive. So it's exactly the same plant that has lasted throughout time. And of course, the famous Glossopteris. You look at the leaves of the Glossopteris and you look at the leaves of the ones that I've just been showing you in the Glossopteris and Gangamopteris. This is the remnant of those early plants in Gondwana. Now to move on to something else, the coals that formed in the Northern Hemisphere versus the coals in the Southern Hemisphere. Just remember the environment, hot, wet environment, very cold, many areas dry. Now, in order to form coal, you need to know what environment your plant's going to form in. Here you have a tree trunk. A tree trunk that is growing or falling and is being captured, if you wish, at the bottom of a pond in anaerobic acidic water will become jellified. It's something like taking your tea leaves, where tea leaves, if you leave free tea leaves, not in a tea bag, you go to your teapot the next morning, you'll find that they're very gluey and very sticky, and basically they also deposit a brown type of jellified material. This is the process of jellification. Now, the French name for jellification is vitrinization. So the name for jellified material is vitrinite. On the other end of your tree, you have those tree trunks or branches that grow in air. Now, in air, the cell contents are decomposed either by fungi or little bacteria, or they dry out completely, they become desiccated. And what you land up with is dry sticks of wood, such as you get on the veld, dried pieces of wood. There is nothing left in it other than tough cellulose and lignin, versus what you have down here, where all the cell protoplasmic material is retained in the plant. And that is where you get very high volatile material staying with it. So the two end points become controlling of the type of area and coal that you're going to form. This area in the middle, where you see the blue and the red, is where you get partial jellification and partial oxidation subject to the water level at the time. The red is known as vitrinite and provides you with bright, shiny coal. The dry material provides you with what is called inertinite. It has another name, fusinite too, but we call it inertinite for the simple reason that when you put it in a fire, certainly in a boiler, it takes a devil of a job to ignite it because there are no volatiles to assist in its ignition. Whereas here you have high volatiles and it'll burn out in next to no time. This material is halfway between the two. South Africa has predominantly the top two. Europe and America have predominantly the bottom one. Those are the major differences between our coals. This is vitrinite. It looks like glass. It behaves like glass. This you see under a microscope. You can't cut it, but it's brittle. It's extremely volatile and very, very favorable for combustion. These are the fusinitized, or if you like, lignin cellulosic pieces of tree trunk that has lost all its volatiles in cytoplasm. Now, these materials are extremely difficult to ignite and combust. I worked on all of Eskom power stations, and these materials, when they are in the coal, come straight up the back end, untouched. Here you have coal bands of coal, which is where your inert materials are formed. There you have your bright bands where your reactive or vitrinite is formed. So we have it, and you can see it in every lump of coal. Now, the practical application, without going into any more detail, is the following. A particle of vitrinite, or the bright shiny material that you have a lot of volatiles in, will burn out, given size X, will burn out in 10 meters. The inertinite particles, that cellulosic lignin, very white material, 15 meters. Now, if you're going to design a boiler for this coal, and you are faced with this coal, guess what happens? The bulk of the coal comes out the back end of the chimney untouched or only partially burnt. This is the problem for Medupi and Kusile. It's as simple as that. This diagram will show you, on the left-hand side, we've got the reactive and highly reactive components in coal, and the inert or semi-inert to totally inert. The German coal, which is representative of coals of the Northern Hemisphere, make up an 85% reactive. The Southern Hemisphere coals, if you're lucky, 20% versus 85%. I rest my case. We have a lot more of this inert material, and of course a lot more mineral matter or ash. We've just been working, I'm not sure if you can see the column to the far right, we've been working in a case, still working with it, where over 75% of the material is so inert, it has actually caused a major explosion in one of the metallurgical plants and literally stopped the processing of the entire manufacturing industry in that area. You have to understand your coal and how to use it. The relevance of coal today. Now, as far as why coal is important to us, highest mining income earner, down at the bottom you will see for the years 2016, 17, and 18. For coal, 216 on the left, the gray is 217, and the orange is 218. In all cases, coal gave a higher return in rands per billion than platinum, gold, iron ore, manganese, or chrome. And the same has continued in 19. Coal provides 91% of our electricity and 81% of the region's energy. It provides 100% of the reductants in the iron, steel, and alloy industry, without which you could not make iron or steel. It provides over 33% of the liquid fuels in the country, petrol, diesel, etc. Over 90% is required for cement production. Over 200 are required, or it gives rise to 200 major chemicals for thousands of carbon-based products. Now, we have the Paris Accord that has come up, and one has to think very carefully about this. This diagram shows you the coal dependency in 2017. South Africa is the third from the bottom, Botswana is the bottom. But the Paris Accord has brought the world together and has managed to get everybody to agree to lower the emissions, which is the right way to go. But coal is, of course, the problem. Part of the problem, shall we say. This, in principle, shows the reason why. Here you have the solar energy coming in. Some of the sun's rays bounce off, some come straight through to the ground, some come straight through and try to bounce back and out, but in fact are stopped by the atmosphere, which is now, it is claimed, getting to be rather thicker in CO2, which rather prevents the heat from coming off. So the heat is trapped in by carbon dioxide. It's not only carbon dioxide, it's water and many other things as well. Carbon dioxide is sourced from burning of fossil fuels, from cars, from airplanes, etc. So there's a lot of work that needs to be done. But there is another factor, a lot of trees have been cut down, which now does not provide you with the oxygen to counteract the CO2. We have to stop that. So in effect, to cut a very long story short, we have to minimize the adverse effects of all these emissions, but we have to maximize on the economic benefits of coal. And these are major benefits. Coal is abundant, storable, which of course is a problem for wind and solar at the moment. Base load, it's there whenever you want it. It's affordable. It's transportable. It's gas can be very dangerous if you transport it. We don't have too much oil to transport anyway, and we don't have significant gas resources. It is responsive to supply and demand. You can turn it on and off. You can't turn the sun and wind on and off. And it provides all those multi-products as well. Without going through, there are 3 different ways of cleaning up coal. Suffice it to say, technologies are in full operation to clean coal up in every respect. There are boilers. The one on the left is the one that Eskom uses. The one on the right is the one they should be using to clean it up, to capture your SOx and NOx, and to provide you with mechanisms to use your CO2. The other emissions like mercury and lead and SOx, etc., now can be captured as well. Multiple technologies exist for this, but people are now realizing that these emissions are a source of very valuable products, and there is now new technology only available in Europe at this point, that one plant, that one in the middle, captures all of these emissions, produces the products at the bottom, and produces, you probably can't see, but on the right-hand side, there's a little blue block that says clean air. So in fact, coal can be cleaned to 98%. And that is basically, Sasol provides I'm not even going to go through it. Just look at the orange boxes. That is what Sasol provides for South Africa. Look at all the products listed there that coal provides for us. Look at the new technologies that can be provided from the carbon, which you could capture from the CO2. And these give rise to aerospace, ceramics, automotive, magnets, ITs, alloys, etc. It's huge. Basically, in effect, coal itself can give rise, and I've only listed some of the products there. The emissions that can be captured can give rise to these products over here, and we can have clean air. Basically, you're looking at increasing value the further you go. Here are your alternative energies and fossil fuel. Alternative energies cannot give you more than power unless you have water and you can have some value added end products, but we don't have too much water. Coal can give you direct power, indirect power, and all the products that we were talking about before. My last slide, my very last slide, the future. Coal is arguably the most valuable mineral commodity this country has in its arsenal. The challenge is to use it responsibly and appropriately for as long as it is available to us. Thank you, John. That's my little spiel.
Thank you very much indeed, Rosemary. Very stimulating. Took us through over ages and through a vast number of different subject matters, just showing how well your geology and botany combine. So now, are you, Rosemary, prepared to take some questions?
Yes, of course, with pleasure.
So if you'd like to ask a question, either unmute yourself or type something in the chat box and we'll give that question to Rosemary. So can I ask any questions from anybody?
Close to me. Come and sit close to me and I can ask you questions.
Hello, Lionel.
There is Lionel. Come and sit closer. There we go.
Rosemary says I've got to sit closer.
You can help answer any awkward questions.
Any questions, anybody?
How do you put your hand up?
Anthony?
Look, John, can you hear me? Tony Shardlow.
Yes.
Carry on.
Rosemary, Am I understanding then that Eskom has got the wrong equipment for the coal that they're using?
Absolutely. Absolutely, John. Absolutely. Eskom started, Eskom started looking at these new boilers that I've very fleetingly passed by about 10 years ago. And they decided at that time they'd rather stick with what they knew. But what they did not realize at the time, that export was going to be taking the better quality coals and they would be landed with the worst quality coals, which do not work in the technologies that they have now. Whereas that new technology can take discard, it can take rubbish, it can take municipal waste, it can take very bad quality coal and still get heat out of it. So they were very unwise by not taking it at that time. They were ill-advised.
Now, is this all part of crookery, or is it just developmental?
No, this is not crookery. This is lack of education, lack of acceptance of certain proposals. This had nothing to do with me. There were people bringing in this new technology. We are probably the last country, reasonably advanced country in the world, that does not have that technology. There are thousands of these, they call them circulating fluidized beds, now being put into the Far East. All over the Far East, India, China, Vietnam, you name it, Indonesia, all over. But we have not got one yet in this country. In fact, we are just working with people who are beginning to put one in Mozambique. Botswana is thinking of putting two up. They had one which was ill-designed, but they're putting up another one. So other countries are putting them up. Not us. It's very sad because we could be using the very poor quality coal that is now being left to us, whilst the rest, Lana will tell you more about the the marketing thereof.
That's a long story.
Rosemary, can I ask a question, please?
Yes, Peter, go ahead.
I gather that the boiler tubes in Kusini and Medupi have to be changed. Could Rosemary give us some idea what they're changing them for and why they're getting changed?
Yes, probably abrasion and corrosion, because the nature of the coal going in now has a lot of quartz involved. Quartz doesn't melt until it gets to a temperature of about 16 to 1800. So it is bouncing around in those boilers and corroding them and eroding them unbelievably. And a lot of people are throwing in the discard coal, as well as a little bit of rock here and there, if not a little bit more than a little bit of rock here and there. No, they are being sold a pup on many occasions. That is where the problem arises for the not very good practices that are happening at the moment.
Thank you.
It's very surprising that South Africa has very few research facilities.
That's my greatest sadness. It's my greatest sadness, if I may put it very bluntly, and I might hurt a few people here. This is a hard rock country, and it's predominantly mining with a fair smack of metallurgical production. But when it comes to soft rock or coal material, there is nothing. The Chamber of Mines does not go beyond the mine gate. They have a huge research arm that does not go beyond the mine gate. Eskom has its own research arm, and a very good one at that, but it does not help 4,000 to 6,000 other users of coal in the country, and is unable to persuade their management where they should be going because of political influence. And we don't have a research center that is recognized as a major center that brings new technologies into this country. In 1994, not necessarily because of 94, but it happened at that time, that 4 major coal research laboratories were closed at that time. None have been replaced. You have commercial laboratories that will do analyses for you. They do not do research. They do not bring in new technology. They do not bring in new innovation or test for that. They're not allowed to by law. I have to tell you, it is the saddest, most frustrating thing that anybody could be in. I battled through 12 to 14 years in the chair of the Clean Coal Technology, working with government who are being paid huge amounts of money by, and I mean huge amounts of money, by the renewables. There is a move to say that wind can literally provide every megajoule that you require in this country, because the wind is blowing somewhere at any one point in time. What they fail to understand is that what this does to the grid and to the actual distribution of the energy and the ramping up and the thousands of kilometers that that will have to travel is not possible. This, sorry, John, I shouldn't go on, but can I just make one more point here? I've just been reading articles. California has more blackouts and load shedding than we do, and they are almost fully renewable. South Australia is exactly the same, and the price of their electricity has gone sky high. They've all closed their coal power stations down. Let me get off my high horse. Doesn't mean to say you can't have renewables. Of course you need renewables to back it up, but you cannot do it without base load in the background. There should be both.
Rosemary, there's a question from Christine. If our coal is bad, should we not be going nuclear? I think that's the subject of a whole new talk, actually, isn't it?
Let me answer that very briefly. I'm very much in favor of nuclear. I was working with people that had the pebble bed reactor. I'm sure, Rob, you had something to do with that as well. Pebble bed reactor was a South African development which then ceased to function and is then taken up by, Rob, would I be correct in saying America, and should be brought back, but it cannot do everything the country needs. It needs to be part of the base load again. Coal will not be there forever.
I think that's really the summary, isn't it? Really, you need a bit of everything, and coal is the basis of so many other things besides energy.
Absolutely.
All the things that John knows about with Sasol. Yeah. Okay,
Yes.
I think we've gone past our time, so we should really now ask Lilith to give a vote of thanks. Lilith, over to you.
Thank you, Rob. Can you hear me?
Indeed.
Can you hear me?
Speak up.
Thank you, Rosemary. That was a tour de force. Who else has in their midst, actually one of us, somebody with such knowledge and ability to describe a vast geological era in an hour? You really were amazing. And such a, probably the most important geological era, because it is so topical and so relevant. Think of yesterday, think of today, think of probably forever with our blackouts. And for me personally, you brought back such memories. I just have to tell you that whatever it was, 65 years ago, I sat on the edge of the bench at Varsity. Absolutely, my mind was blown with the Dwight Ice Age. I sat there thinking of kilometers, as you've told us, kilometers of ice flowing from the north, which again, you've told us, the north was always hot. How could an ice sheet come from the north? Flowing down and grinding mountains in its path. And to me, it's so relevant because you go to the Waterberg today and you see the Seven Sisters, all the same round height. Go to Hartbeespoort this weekend, Hartbeespoort Dam, and look left, look right. and you see the hills all the same height. That was that ice sheet. Then it went down to Kimberley, and it glaciated a pavement in the riverbed, which the Khoi and the San subsequently used as a canvas for their designs. Finally, via the Swartberg, it started melting. The big meltdown was at what is actually called Dwika, near Langsberg. And there all the exotic rocks tumbled out and crushed material, and all that we can see today, all around us at the end of this ice age. And you've painted such a vivid picture for us that I was taken back 65 years. Thank you. Those were some gardens all those millions of years ago. Thank you again from all of us.